Hi everyone, Mr. Lee here. In this video, we're going to go over instantaneous velocity and instantaneous speed. Alright, let's begin. So before we actually get into the definition of instantaneous velocity and instantaneous speed, I want to do a quick review of average velocity and average speed. So let's start off with the equation for average velocity, which we determined was the velocity, which is a vector, that's what the arrow means, is the change in position divided by the change in time, so displacement over time. And we also learned that for speed, it's going to be your distance divided by time. As a quick reminder, displacement and distance are not the same. Distance tells us the total magnitude traveled, and displacement tells us the shortest, the shortest distance between 2 points, your start and your end. Okay, so this is average velocity and average speed, and with that we came up with how we can express this using graphs. So let's do the graphical definition of average velocity. So if I have a position versus time graph, I'm going to lower that a little bit. So if we have a position versus time graph, okay, and we have a function that looks something like this. So we say alright, so that's our function for a object that is moving. Okay, so this is an object that moved forward and then backwards. So this is our position versus time graph. Right, so let's do a quick reminder of what we can gain from position versus time graphs. And the first one is the idea of slope. So if you remember from your math classes, slope is your rise over your run. Okay, and your rise is the change in the y-axis over the change in your x-axis. So if we take a look here, our change in our y-axis was our displacement. So for this one, we can say it was our displacement divided by the change in our x-axis, which is delta t. Now you might be thinking, whoa, delta x is also in this equation here, but remember this x is the x-axis variable. Okay, it is not position. This right here is displacement. This is the variable itself. All right, and we know that delta x over delta t is equal to velocity. So we can safely say that the slope for a position versus time graph gives us velocity. So that's a good reminder, because I want to remind ourselves of how we found average velocity for a graph like so. So let's say we wanted to find the average velocity between two time intervals. Let's say this is time interval 1, okay, TF, and let's say this one over here. So this will be TO. So in order to find the average velocity between these 2 points, okay, what you would need to do is you would need to create a line that goes through those 2 points. And let me try my best here to connect those 2 dots. All right, there we go. All right, so you would create a line that goes through those 2 points, and that line, finding the slope of this line, would give you your average velocity. Okay, and we can see here that because it's downward sloping, this will be a negative average velocity. But let's say we wanted to have the average velocity of 2 time intervals that are a little bit closer. Okay, and let's say we wanted to find the average velocity between this point here. So I'm going to call this TF prime and this right here T initial prime. Okay, so we wanted to find the average velocity for those 2 points. And by and when we do this, notice that our delta t has shrunk a little bit. So what I'm saying is that our delta t in our velocity equation, okay, this is getting closer to each other, meaning TF and T initial are getting closer together. All right, and so if we were to do that, okay, we want to do the same strategy here, and we want to connect the 2 points. Whoop, okay, and whatever the slope of this line is will be your V average for these 2 time intervals. Okay, now the reason why we're doing this is this will help us to find instantaneous velocity. So average velocity tells us the average motion between two time intervals, but as the name implies, for instantaneous velocity, we want to know how fast an object is moving at a very specific one time interval. And let's say this is that one time interval. I want to know how fast the object is moving at that time, okay? At that time. And so we can say that this is, we'll just say that this is t. We want to know how fast it's moving at that part. Now, in order to do that, the technique is to get your average velocities, okay, and you want to shrink your TF and your T0 closer and closer and closer together until they are so close. So I'm going to try to get it as close together as possible. Okay, so we got it closer together, right, and then we can find our average velocity there. Okay, and then we want to get closer together even more. I'm running out of colors, right? We want to get closer together even more. I'm not going to do that one because it's going to go into the point. So we want to shrink TF and T0 so that they're basically the same. So instantaneous velocity tells us that our T is basically just T. There is no TF, there is no T0, it is just T. So we're shrinking the average time until we get to a single point. And when we find that single point, okay, the strategy is the same. If you were to find the slope of that single point, okay, that single point, that will tell you, the slope will tell you the instantaneous velocity. Now, this goes with the definition of the different lines that we created. When the lines go through 2 points, this is what we call a secant line. A secant line. A secant line. When the line goes through multiple points on a function, well, 2 points. And so for our secant lines, they all give you the average. However, when we find a tangent line, and tangent just means that your line is touching one part of the function, this gives you your instantaneous velocity. Okay? All right. Now, the reason why I wanted to go through all that to start off is because it actually helps us come up with the definition or the equation of instantaneous velocity. So I'm going to show you the calculus of it first. Let me see if I could remove this away. There we go. So the calculus definition of instantaneous velocity is if you were to find the derivative of a position function with respect to time. Okay, this gives you your instantaneous velocity. Okay, and this is something that we will use time and time again. So I'm going to galaxy star that because that's very important. All right. So I want to break this down because we will see this form multiple different ways. So what this tells us here is, so this is dt, which is the difference in time. So this is saying that your delta t gets close together. Okay, and by that I mean that your t final and your t initial are basically the same. Okay, are basically the same. Right? And this dx over on the top, so this is telling us that we are finding the change in position. Okay, so this is, we're finding the change in position, but because we're finding the change in position for such a small period of time, okay, that change in position is very, 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 very small. So what that means here is that our change in position was from this point to this point. Okay, a very large change in position. Or here, this will be from here to here, very large. But if we shrink this down time and time and time and time again, we get to a single point. Okay, or what we can imagine to be a single point. And so this is telling us that we're finding the change in position with respect to time. Okay, so this just shows us the instantaneous position at a very instantaneous period of time, or how fast it's going to be moving with respect to time. So that's a nice definition and all, but I like to, of course, get some examples in you so that we can actually see what this means. So let's say that we are given a function, a position time graph, and let's say it's 4 That shouldn't be x, that should be t. Okay, and we want t as a variable because that's the independent variable within the function. 4t squared plus 2t minus 7. Okay, so this is our position function. And so we have an object that is moving, and that motion can be described with this equation, right? In order to find how fast it's moving at any given point, we can take the first derivative. So we say dx dt. So all we're doing is taking the derivative, and we can just use the power rule here. So 2 times 4 gives us 8. T, 2 minus 1 gives us 1. So we'll put 1 there. Plus. All right, so technically there's a 1 here. So 1 times 2 gives us 2. Over here, our exponent is technically a 1. So 1 minus 1 gives us 0. And any variable to the 0th power just gives us 1. So 2 times 1 just gives us 2. So I'll leave that as 2. And here, there is no variable here, so that will just be 0. All right, so for this position versus time function, okay, this position function with respect to time has a velocity with respect to time equal to 8t plus 2. I'm going to get rid of that prime there. So if the problem is asking at time of, let's just make it simple for us, 1 second, where is the object located? Okay, and how fast is it moving? We can use our newly found derivative and our position time function to figure that out. So let's try it. So we say x of 1 is equal to 4. We're going to put 1 in here, so 4 times 1 plus 2 times 1 just gives us 2 minus 7. And we can say that at 1 second, this object is, what is that, at -1 meter. Right? How fast is it moving when it's at -1 meter? Well, we can use this equation. So we can say v sum 1 is equal to 8 times 1, just gives us 8, plus 2, and it's moving at 10 meters per second. So when this object is at -1 meters, it's moving at 10 meters per second. All right, let's try one more. So let's say we have a position time graph of, let's say, -4t cubed plus 2t. Okay, so this is our position versus time graph. I want to show you a different way that derivatives can be represented. That's why we're doing one more. We can say the first derivative. Okay, so this means that we're taking the first derivative of a position time graph. 3 times -4 gives us -12. T, 3 minus 1 gives us 2. Plus, remember, there's technically a 1 here. 1 times 2 gives us 2. T, 1 minus 1 gives us 0. So t to the 0. So that's basically 1, or that is 1, excuse me. So 2 times 1 just gives us 2. All right, and so this is our new velocity function. And same thing, we can say, you know, at time of, I'm going to make it simple for us again. Well, let's do 2 seconds. Okay, at 2 seconds, find x, and so find the position and the velocity. So I'm going to plug in 2. So we get -4, 2 cubed plus 2 times 2. And we get 2, 4, 8 times -4. So -32 plus 2 times 2 is 4. So we can say that the object is at -28 meters at 2 seconds. And for the velocity, okay, so x prime of 2, which is the velocity, we have -12 times 2 squared plus 2. So 2 times 2 is 4. 4 times -12 is -48 plus 2. We get -46 meters per second. Okay, so this is our velocity. All right, so we know that at 2 seconds, the object is moving pretty fast at -46 meters per second. And remember, this negative just means that it's moving in the negative direction. It does not mean if it's fast or slow. And it will be located precisely at -28 meters. All right, so that's how you can use a position versus time function to find the velocity. And if you're given a very specific time to look for, you can now find the position and the time for that time interval. We also went into how we can look at a derivative such as this and what that means in terms of a graph. Remember, you are taking a infinitesimally small amount of time and you're trying to find the function at the smallest amount of time. So that's what the derivative means. All right, I'll see you next time. Bye-bye.